Today we're going to look at the same thing we were doing in the last section of notes where we're applying the sum and difference formulas, so make sure you have your reference sheet and your unit circle handy. But we're going to apply it to the tangent function today, and we're going to look at an example of proof using these formulas. So here are the formulas. Yesterday we focused on cosine and sine functions. Today we're going to focus on the tangent one. You can see it is a bit uglier because it is going to create a fraction out of it. And again, let me stress that if you have two angles that you have picked to add together, then it's going to be an addition on the top, but it's going to be a subtraction on the bottom. So the top sign stays the same, the bottom sign flips. And then same thing if you have a minus, if you picked like 60 minus 45, then on the top you'll have a minus, but on the bottom you'll have a plus. So be careful about what is happening to the signs in the numerator and the denominator. So here's an example where we're asked to evaluate 15 degrees. You'll find that really the only times these formulas are useful are when they give you the angles like 15 or 75, the ones that are in between the 30-degree gaps. That's really the only major appeal to using these outside of a proof. So for 15 degrees, we already talked about how there are a couple of different ways to solve it. You could either do 60 minus 45, or you could do 45 minus 30. Either way is fine. So this time let's try to use the 45 minus 30 approach. So 45 minus 30 will give me 15. Just make sure you find two angles that either add or subtract to the given one. And make sure that you pick numbers only that are found on your unit circle. Otherwise, this method won't work. So now that I have my two angles specified, from looking at the formulas, it's going to be tangent of the first one minus tangent of the second one over 1 plus tangent of the first one times tangent of the second one. It's very easy to make mistakes on the signs, so have your reference sheet handy while I'm doing this. So in the numerator, we said tangent of the first angle minus tangent of the second angle. The signs on these do not flip. It's the denominator where the signs are going to flip. And then for the bottom, it's 1 plus. That's the sign flipping from being a minus sign to a plus sign. Now I need to multiply tangent of 45 and tangent of 30. So we're going to be evaluating each of these individual functions separately and then seeing what we can do operation-wise between adding them, subtracting them, etc. So having your unit circle, or if you have your trig chart handy, that would also be tangent of 45 degrees will just equal 1. And then when you're subtracting, we're going to have minus tangent of 30 degrees, which is square root of 3 over 3. And in the bottom, that's going to be 1 plus, and it's going to be those same two numbers. So since we already applied them or evaluated them, we said tangent of 45 degrees is equal to 1. And then tangent of 30 is equal to square root of 3 over 3. We're going to try to simplify this more if possible. Notice on the bottom that 1 times square root of 3 over 3 is just square root of 3 over 3. That multiplying by 1 doesn't change anything. And as a bit of a shortcut, recognizing that in the numerator you have a denominator 3 and in the denominator you have a denominator of 3, if we multiply both top and bottom of the fraction by 3 in this case, it would actually clear out the fractions inside of fractions. And the reason I'm allowed to do this is because multiplying by 3 over 3 is equal to 1. So I'm not changing the value of this, I'm going to change the form that it's in. So if I perform that operation, multiplying by 3 over 3, now I'm going to have 3 minus root 3 over 3 plus root 3. So I'm just distributing the 3 through. 3 times 1, 3 times negative root 3 over 3. And then in the bottom, 3 times 1, 3 times root 3 over 3. Unfortunately, we have talked about having to rationalize our answers, and I do see a radical in the denominator here. So to get rid of that, we need to multiply top and bottom by the conjugate. So it's the simplifying of these problems that makes them the worst. So the conjugate is just changing the sign in the middle. So I'm going to multiply top and bottom by 3 minus root 3. So if you use the shortcut, because we have the same binomial squared essentially, so the shortcut is a squared plus 2ab plus b squared. In the denominator, I don't have the same thing squared. I have 3 plus root 3 and 3 minus root 3 being multiplied. So for this, there's a shortcut in that you don't have to do the whole distribution because the outside and inside products would actually cancel out. So all you have to worry about is first times first and last times last. So it's a nice time saver if you recognize the number times its conjugate, you only have to do the first and the last products. And then there's still a little bit more simplifying I can do here because the 9 minus 3 in the denominator is just equal to 6, and the 9 plus 3 on top is equal to 12. And since everything here, all three of these terms are divisible by 6, I can divide all of them by 6. Don't make the mistake of just canceling the 6 from this piece in the top right. There is a plus or a minus on top, so you have to take it from both of these terms in the numerator. So you actually end up with a final answer of 2 minus root 3. Now, looking through that problem, it was a lot of work, but the only new thing I'm actually teaching you is this part up here, how to split the tangent into this expression. We've already done evaluating the individual functions like tangent of 45 degrees, tangent of 30 degrees, so that shouldn't be new. And then all of this stuff here where you're trying to get rid of fractions and rationalize your denominator, that should all be skills from algebra and algebra 2. So now we're going to look at a proof. If they ever give you an expression, and usually they use what look like the cofunction identities, we're going to prove why this is true. This is basically saying that cosine and sine are the same function, they're just shifted over a little bit. Specifically, they're shifted over pi over 2. And we're going to prove that using our sum and difference identities in this case. So they've actually set up one of the sum and difference formulas for us here. We have cosine, and then they're saying do this angle minus the other angle. So if you're looking at our reference sheet, that means I'm going to be using this top line here, and I'm going to be treating the cosine of x minus y. That's going to be the pi over 2 and the x. Confusingly enough, x is going to be y in this case. So we're just going to split that up as cosine times cosine, and then sine times sine. Remember that the signs flip for the cosine sum and difference formulas. So this will be cosine of pi over 2 times cosine of x. And then the sign's flipping from being a minus sign, so plus sine of pi over 2 sine of x. Well, if you look at the reference sheet, then cosine of pi over 2, the x-coordinate at pi over 2, is actually equal to 0. So that's going to cancel out whatever this other value is. Even though we can't evaluate cosine of x because they have a variable in there, it doesn't matter what the variable is because we're multiplying it by 0. So the answer to that is 0. On the right-hand side, if you're looking at sine of pi over 2, so the y-coordinate at pi over 2, that value is equal to 1. And so again, I don't know what the variable is for x, but I know that multiplying something by 1 does not change its value. So I'm ending up with 0 plus sine of x, which is just equal to sine of x. So by telling you that the sum and difference formulas are true, we have now just proven why sine and cosine are shifts. They are phase shifts to the left or to the right of each other, a distance of pi over 2. So that's the completion of our proof. We've made the left side match what was on the right-hand side of the equation. And that's all for the notes. Thank you.